The improvised outcome of the Rutherford model is the Bohr's atomic model. Bohr's theory could successfully explain the stability of an atom as well as the discontinuous spectra of the hydrogen atom. To understand the Bohr's atomic model, it is necessary to acquaint ourselves with the nature of electromagnetic radiation. The underlying principle behind the Bohr's atomic model is the quantization of energy or radiation. The underlying principle, sorry, Bohr's atomic model is the quantization of energy, which is explained pattern of our discussion. Energy can be transmitted through space by electromagnetic radiations. These electromagnetic radiations are the best described in the terminology of waves. The wave nature of electromagnetic radiation is established in 1870 by James Clerk Maxwell. Let us now understand the general characteristics of wave in an object produce a series of waves when it vibrates continuously. However, the vibration of motion of charged particle like electron produce a produce a wave train of oscillating electric field and magnetic field. Waves which are produced to the periodic motion of charged particle such as electron are called electromagnetic waves. This is suggested by James Maxwell. Note that the name electromagnetic radiation is attributed to the wave that consists of oscillating electrical and magnetic properties. An electromagnetic wave be represented as shown. To characterize a wave, we need to specify its properties such as wavelength, frequency of the and wave number. The wavelength is the distance between two successive the wavelength is the distance between two successive crust or trough of a wave. Wavelength is denoted by Greek letter lambda. It is expressed in either centimeter, all the meters, or in angstrom units. The next characteristics of a wave is the frequency. Frequency is the number of waves that pass a given point in 1 second. It is denoted by the symbol nu and is expressed in hertz. Velocity of a wave is called or defined as the distance traveled by a wave in 1 second. It is denoted by c and is expressed in centimeter per second. Let us now understand the relation between the wavelength and velocity of a wave. As frequency is the number of waves passing through a point per second, and wavelength is the length of each wave. Their product will give the velocity of the wave. The electromagnetic wave travel through empty space with the velocity of light. The last characteristics of a wave is the wave number, which is defined as the number of wavelength per unit length. It is denoted by the symbol nu and given by the equation nu bar equal 1 by lambda per centimeter. Let us now solve a numerical problem on the basis of characteristics of a wave. Calculate the wave number and frequency of violet radiation having wavelength 4000 angstrom. First, Let us calculate the wave number. The first step involves writing the formula to calculate wave number. That is, the number equal 1 by lambda. The given lambda value is 4000 angstrom. Well, 24 multiplied by 10 raised to the power minus 7 meter. The second step involves substituting the value of lambda in this equation. On solving, we get nu bar is equal to 2.5 multiplied by 10 to the power of 6 meter, or 2.5 multiplied by 10 raised to the power 4 centimeter. Now let us calculate the frequency of violet radiation. The first step involving writing the corresponding formula nu equal to C divided by lambda. The second step involves substituting the value of lambda, that is 4 multiplied by raised to the power of minus 7 meter, and velocity of radiation, which is equal to 3 multiplied by raised to the power 8 meter per second in the given equation. On solving, finally we will get 7.5 into 10 to the power 14 per second. Now let's look at certain key properties of electromagnetic waves. Electromagnetic radiation. As shown, is a form of energy that consists of alternating electric and magnetic field producing by oscillating charged particles are perpendicular to each other to the direction of propagation of radiation. Unlike sound or water waves that require a medium for propagation, electromagnetic wave can move in vacuum at the velocity of light, that is 3 into 10 raised to the power 8 meter per second. All electromagnetic waves travel with the same velocity but differ from one another in wavelength, and therefore in frequency. Let us have a look at the arrangement of different electromagnetic radiation in increasing order of their wavelength or in decreasing order of their frequencies. When these electromagnetic waves of different wavelength are arranged in the order of increasing wavelength or decreasing frequency, it is called electromagnetic spectrum. Of these, the radiation that are visible to the naked eye constitute the visible spectrum. The frequency range of the visible phase is 3.9 into 10 to the power 14 to 7.9 into 10 to the power 14 Hertz. The region above the violet color is called the ultraviolet region and has a frequency equal to 7.9 into 10 to the power 14 to 3.4 into 10 to the power 16 Hertz. A region below the red color is called the infrared region, and the frequency of the wave of this region is 3 into 10 to the power 11 to 3.9 into 10 to the power 14. Ultraviolet and infrared rays are not visible to the naked eye. Other important regions in the electromagnetic spectrum include radio waves with frequency less than 10 to the power 9 and microwave with frequency of 10 to the power 9 to 10 to the power 11 Hz. Radio waves have the longest wavelength. In the electromagnetic spectrum, radio frequency region around 10 to the power past 6 Hz is used for broadcasting. Microwave region around 10 to the power 10 is used for radar. Two other kind of electromagnetic wave are X-ray and gamma rays. The wave nature of electromagnetic radiation successfully explains the phenomena of interference and diffraction. But the phenomena of black body radiation, photoelectric effect, and the spectra of atoms were not explained. These things, these things could be explained only if the radiation is assumed to be a stream of photon. That is by considering particle nature. Let's understand these phenomena one by one. Let us understand the phenomena of the black body radiation, which was given by Max Planck in 1900. In general, when radiation strike any surface of the body, parts of it, reflected part of it, absorbed and part of it is transmitted. For example, when an iron rod is heated, at first turns red. As the temperature is further increased, it becomes yellow, then light, and finally turns blue. This actually shows that the radiation is emitted in the order of increasing frequency. Red light being of lower frequency and blue light being of higher frequency of visible region. On the contrary, an ideal black body is a perfect absorber and emitter of radiation. A blackened metallic surface or a hollow sphere blackened inside with a small opening behave almost as a black body. Any type of radiation that enters this small opening get reflected multiple times within the sphere until all the energy is absorbed. Thus, a black body is not only a perfect absorber of radiant energy, but also a perfect radiator. Black body radiate a maximum amount of energy at a given temperature. Note that radiates the same amount of energy it is as absorbed. From the graph shown here, it is visible that at a given temperature, the intensity of radiation emitted increases with decrease in wavelength, reaches a maximum value at a particular wavelength, and then start decreasing with further decrease in wavelength. We see that as a given temperature, wavelength at which the maximum intensity of radiation is emitted, but the position of this maximum intensity shift towards higher wavelength with decrease in temperature. These observations could not explain by the electromagnetic wave theory of light. To account for these experimental observations, Max Planck in 1900 proposed that radiant energy is emitted or absorbed discontinuously in the form of discrete packets of bundle of energies and not continuously. This is the first postulate of Max Planck theory. Planck called these discrete quantities or packet as quanta. Quantum is the smallest quantity of energy absorbed or emitted in the form of electromagnetic radiation. This means that the light radiations absorbed or emitted by atoms, all molecule comprises a stream of quanta. Continuous waves as shown according to the second postulate, amount of energy associated with the quantum of energy is proportional to the frequency of radiation. It is proportional to nu or E equal h multiplied by nu, where E is the energy of the radiation and h is the Planck's constant. 6.625 into 10 to the power of minus 34 joule seconds, and nu is the frequency of radiation. To write this equation in terms of velocity wavelength, substitute the equation to that nu is equal to c by lambda in the above equation. Hence, the resultant equation is E equal to h multiplied by c divided by lambda. The third postulate says that the total amount of energy emitted or absorbed by a body will be a whole number multiple of quanta, that is equal to h nu. This means that an atom or molecule can absorb or emit either one quantum of energy or any whole number multiple of quanta. Note that only certain values of energies are permitted. This is called the quantization of energy. Now, let us solve a numerical problem based on quantum calculation. Calculate the magnitude of the energy of 1 mole of photon of radiation whose frequency is 4.96 into 10 to the power 14 second inverse. First step involving writing the expression for the energy associated with one photon, that is equal to h nu. In the second step, the value of each, that is 6.626 multiplied by 10 raised to the power of minus 34 joule second, and the given value of frequency, that is 4.96 into 10 to the power 4 second inverse. Computing and solving, finally we will get 3.286 into 10 to the power minus 19 joules. The third step involving writing the expression to calculate the energy associated with 1 mole of photon, that is E is equal to n h nu. Here n is the 1 mole, that is 6.0 into 10 to the power 10, 6023 into 10 to the power 23. On substituting the value of, we will get equal 19.788 into 10 to the power 4 joule second inverse. Energy of 1 mole of photon, that is equal to 197.882 kg mole inverse. The previous model, we have learned about the emission of radiation from a black body on the basis of particle nature. Now let us look at the photoelectric effect, which is also explained on the basis of particle nature. In 1887, Hertz performed an experiment in which he observed that when the surface of certain metals such as cesium, potassium, sodium, rubidium, and so on are exposed to a beam of light, as shown, electrons were ejected. This is called the photoelectric effect. The electron thus emitted our current. Photoelectrons don't this experiment. The following observations were made on one number of electrons are ejected from a metal. If the incident light frequency of less than a certain minimum frequency called threshold frequency, the number of photoelectrons ejected is directly proportional to the intensity or brightness of the incident light. The kinetic energy of the ejected electron is directly proportional to the frequency of the incident light. This observation could not be explained using the law of classical physics. to which the number of electrons ejected and kinetic energy associated with these electrons depends on the intensity of the light radiation. However, it is observed that the kinetic energy of the ejected electron depends upon the frequency of the incident light, but not only on the intensity of light radiation. For example, when the metal potassium is irradiated with high intense red light having frequency of 4.3 to 4.6 multiplied by 10 raised to the power 14 Hz. For us together, no electron is ejected, but as soon as it is irradiated with even less intense light having frequency of 5.1 to 5.2 multiplied raised to the power of 14 Hz, photoelectrons are ejected. This is because the threshold frequency for potassium metal is 5.0 multiplied by 14 Hz. Einstein explained these observations of the photoelectric effect for which he received the Nobel Prize in 1921. He has taken into account the Planck quantum theory of electromagnetic radiation for explaining the photoelectric effect. Note that the quanta were explained called photons by Einstein. According to Einstein, electron and metals are held together by attractive force by the metal kernels, that is the positive ions of the metal. To overcome these forces, the photon of incident light must possess a certain minimum energy so as to release an electron from the metal. The surface. Thus, when a photon of sufficient energy strikes an electron in the atom of the metal, it transfers its energy. That the energy of the incident photon is directly proportional to the frequency of the incident light. The minimum frequency that provide enough energy just to release an electron from the surface of metal is called the threshold frequency, designated as nu. When a beam of light, that is a beam of photon, strike the surface of metal, receive is equal to h nu. V greater than V naught, minimum energy required E is equal to h nu naught. HV greater than HV naught. HV minus HV naught is equal to kinetic energy of the ejected electron. HV minus V naught is equal to half mv square. M is equal to mass of electron, V is equal to velocity of the ejected electron. And rearranging the equation, we get each nu is equal to h nu naught plus half mv squared. Nu naught is constant for a particular metal, is designated as W naught, which is called work function. Now the equation in term of work function is shown as, that is observed the value of work function for a few metals. Hence, if the energy possessed by the photon is high, the energy transferred to the electron is also high, and hence the kinetic energy of the electron is also high. In other words, greater is the frequency of the incident light, greater is the kinetic energy of the ejected electron as shown in this graph. Lastly, greater is the intensity of incident light or the number of photons that strike a metal, greater is the number of electrons ejected. For example, when more or less intense yellow light is made to shine on potassium metal separately, then relatively more number of electrons will be ejected from the potassium metal with high intensive light. Now Let us solve a numerical problem based on photoelectric effect. Calculate the kinetic energy of an electron emitted from a surface of a metal when radiation of frequency 5.5 into 10 to the power 17 second inverse hits the metal. The work function of the metal is 3.62 into 10 to the power minus 12 arch. The first step involves writing the given data as shown and then writing the appropriate equation to calculate the given problem. In the second step, let us substitute the value of h nu and w naught in the equation. On solving, we will get the answer as 3.63 into 10 to the power minus 9 arch. The electron will be emitted with the kinetic energy of 3.63 into 10 to the power minus 9 arch. Thus, these theories and conclusions such as the blackbody radiation and the photoelectric effect led to the development of further Bohr's model of atom. Bohr's model of an atom could successfully explain the line spectrum of hydrogen atom that you will learn about in the next module. Before we begin to learn about atomic spectrum, let us understand the term spectrum. When every of white light from the sun or an incident lamp is passed through a prism, it is dispersed into a continuous array of 7 colors, namely Vibgyor. This is called spectrum. It is observed in that spectrum the radiation with lower wavelength bends more than the radiation with higher wavelength. That is why we see violet with lower wavelength at 400 nanometer and red light with higher wavelength at 700 nanometer. In the spectrum, the most common example of spectrum visible to naked eye is rainbow, consists of 7 colors that constitute the white light. These color band into each other. Therefore, the spectrum of ordinary white light is called continuous spectrum. Electromagnetic radiation include a range of wavelength, and this array of wavelength is referred to as electromagnetic radiation or spectrum. When electromagnetic radiation interact with matter, atom and molecule, they absorb some part of radiation and go to a higher unstable energy state called excited state. As the atoms are unstable in their excited state, they tend to revert to its original state and hold gold ground state. By emitting the same amount of energy that is had absorbed earlier, this energy can be emitted in a single step or in a number of steps. Depending on the amount of energy emitted, a radiation of particular is obtained. The spectrum of radiation emitted by an atom is called emission spectrum. It contrasts to the continuous spectrum of white light, and emission spectrum is usually discontinuous with dark spaces between the bright lines. Such a spectrum is called line spectrum. The bright lines in the emission spectrum exist due to the fact that emitted radiation are only of specific wavelength rather than a continuous spread of wavelength as in case of white light. A photographic negative of emission spectrum is the absorption spectrum. An absorption spectrum is recorded by the passing a continuous of radiation through a sample which absorbs radiation of certain wavelength. The missing wavelength that correspond to the radiation absorbed by the matter leave dark spaces in the bright continuous spectrum. Unlike emission spectrum, absorption spectrum consists of a series of dark lines in the bright continuous spectrum. This study of emission or absorption spectrum to determine the molecular structure is referred to as spectroscopy. The emission spectrum is also called atomic spectra, sometimes because Each atom has a unique emission spectrum, like each human being has unique fingerprints. The characteristics lines in atomic spectra can therefore be used in chemical analysis to identify unknown atoms. German chemist Robert Bunsen was one of the first investigators who used atomic spectra to identify elements like rubidium, cesium, thallium, indium, and gallium and scandium were discovered when their minerals were analyzed by the spectroscopic method. The presence of helium was also detected in the sun by the mean of spectroscopic method. Let us study the line spectrum of hydrogen, which is one electron system. 1. When an electron discharge is passed through hydrogen gas, nitrogen molecules dissociate to produce energetic excited hydrogen atoms. These excited atoms emit electromagnetic radiation of discrete frequencies. While getting back to lower energy level, the resultant hydrogen spectrum dominates of multiple series of lines. These are named after their discoverers. The first series in the hydrogen atomic spectrum, Balmer series, were discovered by John Jacob Balmer in 1885. Its lines belong to the visible spectrum of electromagnetic radiation. These are observed when the electron jump from n greater than or equal to 3 to n equal to 2 principal energy levels. If spectral lines expressed in terms of wave number, then the visible lines of the hydrogen spectrum obey the formula wave number nu is equal to nu bar equal to 1,09,677 multiplied by 1 by 2 square minus 1 divided by n square per centimeter. Here n is an integer equal to 345 etc. Balmer formula inspired the Swedish spectroscopic Johansen Rydberg to come up with a modified formula to describe all series of lines in the hydrogen spectrum. The equation may be written as wave number nu 109677 1 divided by 1 n1 square minus 1 divided by n2 square centimeter inverse. Here n1 is equal to 1, 2 and n2 is equal to n1 plus 1, n1 plus 2 or n1 plus 3 so on. The value 1,09,677 per centimeter is called the Rydberg constant. For hydrogen, the first five series of the lines that corresponds to N1 equal to 1, 2, 3, 4 and 5 are known as Lyman, Balmer, Paschen, Brackett and Funds series respectively. Each of these series shown in the table represent the line spectrum emitted by the electrons of hydrogen atom when they are changed state from N2 to N1 principal energy level. Here N1 and N2 represent the lower and higher energy levels respectively.